And looks like we can start. Welcome back, folks. We're about to finish off week 2 of 16, so we're definitely on our way through the course. And there's a lot of scribbles on the Canvas page this time, several announcements, so let's just go through them one at a time. But before we dive into them, any questions that folks have just right away at the moment? Okay, well, probably the biggest thing to talk about is right at the very bottom. We have our very first exam looming. It's on week 4, but these weeks feel like they sometimes go a little bit faster than expected. And so I tried to stay really on top of things as far as exams go in this course. Before we even make it to week 3, probably on the weekend, maybe Sunday if I'm a little bit behind, but possibly Friday or Saturday morning if I'm a little bit more on top with the grading and such, I'll have information posted down here on exactly the topics that are going to be on exam 3. I'll also include review problems, sample exam questions, either from the textbook, some new documents with brand new problems, and so on. So you can have extra different kinds of resources for studying for the upcoming exam. With what we've done already, pretty much the way I'm going to write my exams will be pretty parallel to the problems that we've actually been doing in class. So if you went to the Blake lecture notes and just did them, they're like worksheets. That's a pretty good exam one review in and of itself. The problems that you do on WebAssign will be a great review, but it looks a little bit weird because you're doing it inside of a homework system. So that's kind of strange and weird in a certain sense. But the quiz problems that we'll be assigning on a weekly basis will also be pretty similar to what real exam questions are going to look like. I'm a pretty big fan of parallelism, so whatever I assigned in the WebAssign homework, I try to write my lectures based around them. And then when we get to the exams, I try to write my exams based around all the material that we've been doing as a class and individually in the homework and quizzes. So that's going to be the idea for the exam one writing. Any questions about exam 1 so far? Okay, the other thing that's kind of complicated about a class like this one, it's a hybrid class with students who come in online through Zoom, students that come in person in the classroom where I'm at currently, is that it can be kind of hard to describe how to take your exam, as strange as that sounds. Well, if you're in the classroom or if you registered for the in-person section, the exam is just going to be right here in the classroom itself. That means on Tuesday, we don't actually have a class. Sometimes people log into Zoom because we just get into that habit. But having a class and an exam for an online section is just too much for one single day. So all we'll be doing on Tuesday is doing the exam for the in-person section and for the online section. As far as the online section goes, I directly emailed everyone through the Canvas system your preferred location for the testing center. And at the very start of this week, probably on Monday, very first thing I want to do is directly email you again the instructions for scheduling your exam, whether it's going to be in the Pocatello Testing Center, Idaho Falls Testing Center, or maybe one of the more remote ones, Twin Falls, Meridian, and so on. If you haven't seen that Canvas message so far, don't hesitate to send me an email for your preferred location, and I'll be getting back to you just to double check. So that's going to be the plan. We'll talk a little bit more about the exam, certainly, when we come back next week. And the other thing on the table is we have our very first quiz posted, but any questions or comments so far? Oh, I think I have one in the chat. June says, will formulas laws be provided for quizzes and exams, or do we need to bring that? You won't need to bring that. It's going to be provided. And thanks for mentioning that. One of the things that I like to do as a very first step when I say post the exam one review materials, let me make this a reminder for myself so I know I do that. Is I like to post this information. That's the Word document. Here, let me clear this out for just a moment. Let's call this is a reminder for me. Oh geez, sorry, I'm having trouble with the computer all of a sudden. Reminder, I find all caps just works for me, so that's the reason for that. And I'll say here, first, this is for the exam one materials I'm going to post. Post the notes that will be included on exam 1 on the last page. So I'll show you exactly what's going to be provided as the formula sheet. You don't need to bring anything to the exam. It'll be just your very last page on the notes. I want to get that posted early so that you're informed the things that you'll have provided and the information that you'll have to have memorized for the purpose of studying. Let me close that out. Other questions at the moment? Thanks for that question there, June. Okay, again, we'll talk a little bit more about the exam on when we come back on Tuesday's class and in Thursday's class. But for the moment, the next big thing is the quizzes. We mentioned we'll have weekly quizzes. We didn't do it last week because week one is typically pretty busy already for a class like this one. But here's what the quiz experience is going to look like. You'll have a due date down below. The due date is always intended to be 1 week away from the day it's officially posted. I usually post them a day early because Thursday is a pretty busy day for me. So you'll usually see these on Wednesday. So think of them as officially posted on the 22nd, but you can get started on them early if you prefer to do so. If you click on the link right here, then it just directs you to a PDF. So click on the PDF. And this is what the quiz looks like for our quiz number 1. It'll be pretty short and sweet. This one has 2 questions, but really just one topic, analyzing and computing 2 different kinds of limits, very similar to the ones that we're doing in the lecture notes today. So this is your opportunity to do a problem that's pretty similar to what's in the WebAssign system. But because this is on paper, it'll give you a really good feel for what does an actual real exam question look like. I'll give you feedback on showing enough steps. We'll be doing the steps in lecture notes, so you'll get a good idea. And other things to mention about the quizzes are, you might have noticed it said, hang on, you might have noticed it said it's out of 10 points. Quizzes solve a couple purposes for us. The first purpose we mentioned is it's to give you a feel for what a real exam question looks like, how to write out your step-by-step solutions, and I give you lots of feedback on each one of your quizzes when I return them to you. But I give you 5 points on default just for turning in the quiz. So the other purpose of the quizzes are, they're really just a participation credit fundamentally. So they're not meant to be really high stakes. It's just you practicing problems that are possibly brand new to you. 5 points are just for participating, sending in your quiz. The other 5 points are for correctness. Another thing to mention, there's lots to talk about with these. It's called a quiz only because I didn't want to call it a homework, because then it's going to be vague if I meant homework in WebAssign or this kind of homework right here. Because it's really not like a close your book, put away your calculator type of quiz, it's open note, open textbook, and all those great things. And as Marie asked, yeah, you can absolutely fill these out digitally, just like we're doing on the lecture notes. That'd be a great way to do them. But really, there's a lot of options. You can, if you like, just take an ordinary sheet of paper, solve the problems that you saw on there on paper. Then you can turn it in, say, in person at the start or end of class if you're here on campus. Or you could scan that quiz, scan it and just upload it when you submit it to the Canvas system. Or you could take a cell phone picture even and just send it to Canvas. And I'm not really picky on how I get them. If you just want to send your complete quiz directly to my ISU email address, that's a fine way to do it as well. In fact, that's how I did it completely last semester, as I just totally asked people to hand these things in directly to my ISU email address because I was learning Canvas and I didn't want to deal with extra things going on, problems that might occur. And thanks for mentioning that, Haley. Haley says she was hoping to do it on Word. You know, I could post the Word file as well, just to assist with that. Let me add that to my reminder list. For quizzes, also post a Word file. So that'll make it a little bit easier to annotate. You won't have to worry about taking screenshots from the PDF and importing it back into Word. That can be tedious. So I'll try to get in the habit of posting both versions. So think of this one as the version that's the easiest one to print out if you decide to print it out, and a Word version if you want to work digitally. So again, there's lots of ways to do these. If you decide to click this out and print it out, work on pen or pencil, that's completely fine. You could just take out a sheet of paper, copy the problem down and solve it as if it's a problem out of a book, for example. You can download the PDF or Word file, annotate it working digitally, and send it in as well. So these are the different methods you can send it in. So either a hard copy or submitting the file directly to Canvas in these different ways, whether you're working digitally or scanning your work. Tyler says, will we go over the quizzes in lecture, or will you provide individual corrections for each quiz? I do, in fact, provide individual corrections. So I'll be giving everyone direct feedback. I'll be, depending on how you submit the quiz, if you gave me a hard copy in class, I'll mark it up with a pen and then just give you back the copy. If you send a copy to Canvas or send one to my IUC email address, whether it's a scan of the work you did or a digital copy of the work you worked on digitally, I'll just pretend like it's another set of notes, make some comments. If there's any corrections or things like that I have to mention, I'll put it on paper. So everyone will get feedback on how you're doing on that kind of problem. What goes a little bit along with that comment again, like I mentioned, the quiz is totally open. It's a take-home quiz. For one, you have an entire week turnaround before it comes to the due date. And the reason for that is you're welcome to work in groups on quizzes. If you have a person that you're studying with in a group, whether it's in person, across Zoom, or maybe you're connecting with someone across Zoom, and even when you're in a different section, I'd say working on these on groups is a great way to learn this kind of stuff, and you're completely welcome to do so. Be sure to write in your own results, and that would be the only thing I would ask. Other comments about quizzes are, you can just directly ask me about quiz. If you're stumped on it, it's really just practice. It's a participation credit. Don't hesitate to ask me about it, say in office hours, things like that. You can send me a direct email question. I'm not sure how to do the second part of quiz 1. Can you show me how to start? And I'll always be happy to help out. So this is pretty much how all the quizzes are going to look. I won't say this every single time. It'll pretty much just be the link to the file. And it'll always be a 1-week turnaround. So they'll be posted on Thursday to be due the very next Thursday. We'll probably end up with about 12 quizzes altogether at the end of the semester. Any other questions so far about quizzes in the course? Okay, so this is pretty much how every filled out week is going to look when we go through Canvas. The sections, you might have noticed it moved around. 2.1 was on week number 1, but we finished it on week number 2, so the document lands wherever week we finish. And at the very end of the week that you see in Canvas will always be the quiz that we're doing for the day, or for the week rather. We'll just be repeating that pattern, so the next week will be the same kind of stuff. This one's only one that's a little bit different because of the exam information, but it'll look pretty similar as we go. So I think I pretty much ran out of things to say. Any questions or comments at all, folks, so far? Yeah, go ahead.
So I haven't checked it, but homework wise on website, we have, I think, like 2 or 3 assignments already up.
Yeah, there's 3 assignments posted on WebAssign, correct?
So we have the 3 assignments on website.
Yeah.
We also have quiz one, exam one. Or
Yes, that's correct. So far on the table, it's just those 3 sections in Canvas, quiz 1 and exam 1 upcoming, as you said. That's right. And also, someone mentioned some, oh, let me get to the chat first, sorry. That's hello to everyone in class, says Haley. Another thing that was mentioned from a student, I forgot who asked about this, but I thought it was a great idea. So thank you to the student who mentioned this. The due dates, I'm going to get in a habit. These are the due dates directly out of WebAssign. I'll post into Canvas as well. So we finished this section here on Tuesday. So the due date is posted here just as a quick reference. So you don't have to log into Canvas to see them. You can get a quick glance. Excuse me, you don't have to log into WebAssign to see the due dates. You can see them at a quick glance from Canvas. I have the due date posted on 2.2 because I intend to finish this one today. This one doesn't have a due date, but I'll post a due date once I know the exact date we're definitely finishing it. We'll be starting section 2.3 today, likely finishing next week. Think of the due dates being posted, meaning that's the most likely than not firm date. It's finalized. We intended to finish it today, so I put a date on it. Other questions at the moment? Okay, thanks for all the questions about this kind of stuff so far. If you ever feel like you logged out of class and then you just suddenly had a question and you're like, oh, dang, it's too late, don't ever hesitate to write an email. Even if that email is really late at night, I check all my emails in the morning, and it's never intrusive. If you send an email at any hour whatsoever, I'll just get to it as soon as possible. The moment you have a question is probably the best time to compose that email and send it out. But here's where we left off on Tuesday's class. Let me fix that window there. Here we go. We did a limit, our first big limit, where we did this purely algebraically. We didn't use any graphing tools whatsoever. And what we're going to do is just extend on this idea. But Ashlyn asks, oh, thanks for mentioning that, Ashlyn. Ashlyn was the one that suggested that change on the Canvas page. And is there any way you can submit it as an assignment so it will do a due date and submit it to the to-do list on Canvas? I bet I could do that as well. So let me think about that. Let me make a screenshot on this and I'll investigate how to make that happen. Thanks for that suggestion as well. And that's a good idea. I mean, the reason I posted this as a quiz, even though it's just a glorified PDF link, I could have put that PDF link on Canvas, is so that it would give you a due date. So seeing those due dates in Canvas is very, very informative. So I'll try to, match up the formatting like that, just like on quiz 1. So let me add this to my list of things to work on. I should have that system going for us before we come back on Monday's class. Thanks again, that's a great suggestion. Well, other questions or comments at the moment? Okay, well, let's take a look at what we did on this problem right here. Really, we've done this limit a lot of different ways. We did it on our first example in the entire semester. This was a screenshot that we just imported from the section 2.1 notes. We wanted to take the limit as x tends towards 1 of the function f of x, and our major observation is as the value of x gets closer and closer to 1 from either side, the y value gets closer and closer to a value of 2. So visually, that's what the limit looked like. But when we do this algebraically, it has a definitely different kind of feel. Algebraically, the major tool we used was we factored. The numerator is x plus 1 times x minus 1. We canceled the factor to get a new function, limit as x tends towards 1 of just x plus 1. And then at that stage, we were allowed to use direct substitution, which just means that number 1 got directly plugged into x right here. So there it goes. And the limit came out as 2, just like we saw on the graph. Our goal is to see how to do these limits, no matter how weird the algebra might get, without ever having to resort to the graph. Although if you did plot the graph of a function like this in Desmos, as you're working along with them on homework, just to get another feel or visual on what's going on, there's no harm done in doing that. Well, let's extend on this going further. The major theorem right here was essentially telling us it was okay to cancel. Sure, we went from a function f of x to a different function h of x, but those functions are identical, except for at one value when x tends towards 1. That means the limit itself is identical, even if we do that kind of cancellation. So using that idea again, let's give this a try. Here's the new function down below. This theorem is just a copy of the one above for easier reference. And let me hide that so we're not looking at too many functions all at once. When we go to take the limit of this function, first observe if you plugged -3 into the denominator, let's cite the calculator just for easy reference. -3 in the denominator would mean -3 squared. Parentheses are required for calculator input like that to get the +9. Minus -3, minus 12. You get a 0 down below. That tells me we have a problem with direct substitution. It is a rational function, but -3 is not in domain. So we cannot determine the value of the limit by just plugging it in this time. We get a 0 down below, so undefined. So here's our new approach. We're just going to redo what we did here, using that last problem as inspiration. Let's factor both the numerator and denominator. So we can say this equals a new limit as x tends towards -3. In the numerator above, well, there's two terms, but it has a greatest common factor of x that we can factor out. And in a certain sense, this is kind of just algebra review at the moment. Factor out x, and we're left behind with an x plus 3. Down below, we have a trinomial, so factoring feels a little bit different. It's going to be a binomial times a binomial. The x squared here, leading terms will be x and x. A negative sign here gives us another hint on the trial and error factorization. Signs have to mix, plus and a minus. So we want two things multiplying to -12, adding up to a -1. Would you agree that maybe a +3 and 4 is a good way to go? Awesome. The fast check is if you multiply here to here, you get to -4x. Here to here, you get positive 3x. Those combine to -x, so that's part of foiling out the whole answer. And positive 3 times -4 produces that -12. So we have a factorization. But now we just redo this step. If you factored it and you see common factors, you can eliminate them. That's the content of this theorem. We are changing the function from one to another, but this theorem allows for that in evaluating limits. So now we've simplified the function to limit as x tends towards -3 of just x divided by x minus 4. This is a nice function. On the far left, it was a rational function, and so is this one. We couldn't use direct substitution on the left-hand side because -3 is not in domain. But this function is different at exactly one point. -3 is in domain. We can just use direct substitution right at this step. So here, use direct substitution. I'll just say sub for substitution. That means the value of x, let me use yellow for this, heading towards -3, we'll just substitute a -3 in those two spots highlighted. We write a new equality, but after we use direct substitution, we drop the whole limiting statement. We're just done with that thing. We'll just say we have -3 divided by -3 minus 4. Then we just simplify. This is -3 divided by -7, reducing to 3/7. And the whole problem ends right at that step. Once we eliminated that problematic factor, that x plus 3, the rest of it just goes really, really fast. It's like a function evaluation at that step. Does that make sense to folks on the technique so far with this one? Okay. Everyone has different kind of skills, different ways you learn best. Some people probably like the way of seeing this visually a little bit better when we're looking into graphs fundamentally, but still other people, this might make sense doing it this way, just purely analytically, just looking at the functions, plugging at the numbers. It's good to see it both ways though, to make the connections. Even if you are purely a learner that learns best like this, make the connection with the visual, and it really helps out connecting all the dots in our mind. So either way we look, when you're learning this stuff for the very first time, might not be a bad idea to just occasionally pick up a calculator, maybe go into Desmos, and plot the thing. We can't do this in an exam setting, so this is a technique we have to get used to doing just on paper with only having a basic scientific calculator to use. But when you're learning this in Desmos, no harm in just saying, look into f of x equals x squared plus 3x, x squared minus x minus 12. Look at where we're setting the limit towards, -3. Make your function values get closer and closer to negative, or hang on, let me look at that. Yeah, -3 on the other end here. Make your function values get closer and closer to -3, and see if you get closer and closer to 3/7. Let's throw that in as well. We want to get closer and closer to a 0.428. Now, the first coordinate is the x-coordinate. We want to get closer to the -3, so I'm a ways out. The second coordinate is the value I'm hoping gets close to 3/7, about 0.428. And notice it's dropping more and more and more. And the closer I get to that -3, I'm pretty close now, the closer and closer we're getting to 0.428. And I can make those numbers as close as we would like just by taking this x value as close to -3 as we'd like on either side. That's pretty close. It matches at 2 decimal places when it's -2.97. Notice though, you can't just drop in -3. It's undefined right at that spot. And like we looked at before, most graphing calculators hide that information. We just had to know there's a hole in the graph right there. Well, from either side, that's the experience of evaluating limits so far. June says, I get this algebraically, but conceptually, a fraction limit confuses me. I thought limits tended towards whole numbers. It turns out the value of the limit could be any number whatsoever, which is another weird thing. The limit could have come out as, say, pi, or square root of 2, or just some random decimal expansion like this one. That's the expansion for 3/7. So yeah, that's a weird thing about limits. I think that point of view was more because we did so much stuff on the graphs and whole numbers just happened to be convenient. Other questions or comments about that so far? Okay, so yeah, I see what you mean. This is really the first limit that came out as a non-integer, a non-whole number. So we're also kind of expanding our landscape of what a limit can really be. Essentially, a limiting value can be any real number whatsoever. We're starting to really see it with this first problem over here. Our goal of these notes is just to practice this several more times, looking to an application. And here's the next really interesting problem to take a look into. It's pretty weird too, because we're taking a different variable of consideration, h. Well, it could be any variable. It could have been a y tends towards -3, and you have y's here. It could be an x. I just happen to like x's, so we see that a lot. Or a random variable like h, p, q, anything like that will be the same kind of algebraic process. Any questions before we give this second one a try? Okay, so like we mentioned before, this is kind of a rundown of different algebraic techniques we're looking into. The major idea for this one was factor. If we factor a rational function, we can simplify it, and that got us through the problem. But this function is a little bit different. That square root you see here means it's not a rational function any longer, even though it's a ratio of two different things. And notice the other problem, when h gets closer and closer to 0, well, direct substitution absolutely does not work. You just get closer and closer to dividing by 0. So we can't directly substitute anything into this problem. Essentially, that's what happens on every single problem in example 4. Weird scenarios that we have to correct through this theorem right here. Well, here's a random thought though. If you see a square root, the idea with this one is you can take this and multiply by the conjugate. It feels pretty random. In all honesty, if I didn't read the textbook, if I didn't know that this was coming, multiplied by the conjugate, I don't think I would have come up with that on the spot. I would have probably just come up blank. I'm not sure how to do this limit. So this is one of those kind of problems where seeing it once is going to help out a lot when you see it again in the homework setting. Conjugates come up. So let's review that right here, what we mean by conjugate. The conjugate of something of the form, let's say, root x plus 3, just as a random example, similar to this one over here. The conjugate of root x plus 3 is root x minus 3. So the word conjugate often comes up in the context of square roots coming up or complex numbers, but we're staying away from complex numbers in this course. And the only thing that happens is you change a positive to a negative to get a conjugate. So let's make this our first step. Do that multiplication. This is the limit. H goes to 0. Root 1 plus h minus 1 divided by h. Let's swap that color to purple just to match up with the comment. The conjugate of this thing would look like this. Multiplied by essentially the number 1, because we can't damage the equality by, say, multiplying just by conjugate. We're multiplying the same thing above and below at the same time. So we'll go root 1 plus h. Conjugate here flips that sign to a positive. And same exact thing in the denominator. So this makes it a conjugate. Probably the question you have is, why should we multiply by the conjugate? It's kind of random how this fixes the problem. But one thing that's going to happen, which might feel like a mathematical miracle, is that factor h will cancel out eventually if we multiply by the conjugate. And that's the name of the game on this one. We can't do that limit until h is gone. And it just so happens that the conjugate is the technique to remove h in the denominator. So let's give this some clean space to focus on this one. We have to multiply across numerator, but in the denominator, I'm going to leave h factored out. So this is how I would write out the denominator. Limit h goes to 0. H multiplying the group, root 1 plus h plus 1. Turns out distributing h into this group doesn't necessarily help us because our goal is to cancel that h right there. We know things cancel better if you factor, so that's kind of what the x was doing. When it was left outside, we could cancel that way. So same thought here, but now the numerator we really have to FOIL. But it's not too bad. When you multiply here to here, a root times a root just gives you the thing on the inside, the so-called radicand. So root 1 plus h times itself is just 1 plus h. Actually, conjugates are nice. There's a lot of cancellations that come into play. So if you know the shortcut here, you might not write out the full FOILing process. But let's write it out just for emphasis to show how that works. Multiply it here and you'll get root 1 plus h times 1 is just plus root 1 plus h. Now keep going, multiply here to here. That's just going to be negative root 1 plus h. And finally, multiply here to here. That will turn into just a minus 1. So that's the full expansion, the FOIL process. And here's the next thing that happens. Those are opposite in sign, and they are both also like terms. They cancel immediately. They're just gone. But if you multiply the conjugate by the conjugate, that's the expectation. You really are only getting 2 terms, and the square root has come off. Also, we have more like terms. Positive 1 cancels off with that negative 1. And we could keep on canceling, but let me write one more step so this doesn't turn into a ton of visual noise. This is now cleaned up a little bit more. Limit as h goes to 0. H divided by h times root 1 plus h plus 1. Now this is the next level of cancellations. You could have done it on this step. That would have been totally fine. But now h by h cancels. Just leaves now a 1 in the numerator left behind. So this is the limit. As h gets closer and closer to 0 of 1 over root 1 plus h plus 1. And we're essentially there now. We can use direct substitution for this particular function. Limit laws say we can take the limit of the numerator versus the denominator. And when we take the limit of the denominator, we saw how the limit goes inside a square root or cube root or any root whatsoever. And then this just becomes a polynomial. The end effect is we're just taking 0 and plugging it in right there to finish the problem. Yeah, exactly. This comes in as 1/4 right after that direct substitution. So let's make that step happen. I'll say here just for a paper trail, direct substitution once again. And this is pretty much how all the problems end. Do something algebraically, which eliminates the problem that you started with, division by 0 there, until you can just directly substitute in your value. So now this is equal to, we can drop the limit statement because now we're plugging in the value, 1 over root 1 plus 0 plus 1. So that's what the direct substitution looks like at that step. And now we're basically at that 1/2 because this is just square root of 1, and square root of 1 is a 1, becomes a 1 over 1 plus 1, coming out as 1/2. But if you did this mental arithmetic going from here to the 1/2, that's okay to take shortcuts like that. I usually connect the dots quite a bit in the notes just to make them a little bit more readable, but you can skip some of these arithmetic steps, and that's no harm done. Well, that's our second big limit. This is kind of a weird one because of the variable h. Actually, h comes back. We're going to see this make a really big comeback in chapter 3 when we go to our next objective, finding slopes of tangent lines, essentially computing derivatives. Somehow, some way, h makes a magic comeback. So this is kind of a warm-up to those longer problems. Well, any last questions at all, folks? Getting the value of 1/2 down here. Okay, watch out for this one when you do the problems on WebAssign. I didn't assign anything like this on the quiz, but this one can come up on WebAssign for a problem. Our goal here today is just to practice some more. So here's another one with h inside of it we'll take a look into. And we'll do a more challenging one where we're taking a limit involving a variable t. That's not too unusual of a limit, really. T sometimes refers to time. And we'll be doing that on this one here. Sorry for the corrections here in red. I had a function here that looked okay, but then when I practice it, it just didn't make sense for the context that I wrote out. So I changed the numbers a little bit to make it feel like a more natural problem. But let's go back to this one here. Part C. Any last questions or thoughts whatsoever on the prior one we finished? Okay, so next adventure on this one, let's hide the one with the fractions for the moment. That one's going to be like the challenge one for the notes. This one, well, I don't see any nice way to factor that at all in the format it is in. There's a little bit of a factorization that happened here with the -25 left off, which is not the most helpful thing. Nothing cancels whatsoever. And there's no square roots, so multiplying by a conjugate is unlikely to help out this time. But actually, this is kind of a cool problem. This is one of those just crank it out type of problems. If you expand that, collect all of your like terms, h should vanish from the numerator, and we should get a value out pretty quickly on this one. Yeah, exactly. Good call. Our goal is to just FOIL this out, and this should resolve itself. So let's say for the method here, nothing crazy like the last step where it was a conjugate. Our major method is just FOIL this time. It's really an acronym, so first, outer, inner, last. That's the major technique on this one. Let's do another strategy. Sometimes when you're writing out an entire limit, this one's not too big, but sometimes the algebra gets pretty big on these things. If you find a way to kind of just divide and conquer on this, it's not a bad strategy. So let's do some scratch work first. -5 times h squared is really just -5 plus h times -5 plus h. We FOIL that out. Some people do this pretty fast without showing the step in the middle, and that's okay to do if you prefer. Distribute -5 to the group on the right, and we get 25 minus 5h. Distribute h to the group on the right, and we get minus 5h plus h squared. So this turns into 25 minus 10h plus h squared. And if you went from here to here, I would say that's awesome. That's a pretty quick shorthand. You would knew that the middle term is doubled for a -10. If you show the stuff in the middle, no harm done either. That's working more carefully, I would say, in my opinion. But we'll just take this algebra here on the margin to the right and substitute it back in over here. So now this is equal to limit h goes to 0 of 25 minus 10h plus h squared minus 25 divided by h. And you don't have to do it that way. The reason I separated this out into chunks is I didn't want to write a limit statement with 1, 2, 3 different lines and a whole bunch of extra stuff all at once. This is just a great way to kind of connect the dots and not write out a whole bunch of stuff for one limit. But now that we're here, notice that's the thing that's going to save the problem. I can't cancel h whatsoever when it's in that format. But once you get rid of terms that don't have h, and you're left with two terms that do involve a factor h, it will cancel out. There's lots of ways to do this if you prefer. You have to be careful if you cancel across an addition or minus sign. H divides both terms. What our author is more likely to do algebraically in this context is to rewrite this as limit h goes to 0 of factor the h out, so h, minus 10 plus h is what you would get, divide by h. And this is the same as canceling h here and here. It just drops a power, eliminating it to around the negative 10 and making your h squared just h power 1. Cancels on this side. And yeah, good call, Haley. This one is now just a negative 10 right at this spot. Any questions, folks, on getting to this step? Okay, we couldn't use direct substitution here, but now this might feel like deja vu. We did something algebraically. It wasn't factoring, it wasn't a conjugate, it was just the FOIL method. We combined our like terms. We did in fact factor here, but it was just pulling out a greatest common factor. But now direct substitution will work. There is no h in the denominator. Let me show it on one more line so we can really see that step in action. Limit h goes to 0 of all that's left behind, negative 10 plus h. Substitute in the limiting value in that spot, and we get negative 10 plus 0. The moment we do the direct substitution, the limit structure is gone. Now it's just an evaluation here. And as you said, we get a negative 10 altogether. So that's our limit on this one. Kind of a nice refreshing problem after the conjugate. The next one is going to be the challenge one, where we have to work pretty carefully algebraically. Really, the only big idea with this one is occasionally fractions come up, and we have to do least common denominator fraction work algebraically. Well, any questions at all, folks, on the part C problem? Okay, let me leave that one here. Now for the next one, again, the idea with this one, the big algebraic technique we're doing essentially as a big algebra review, is this time we need to, let's see, how should we phrase this? Find the least common denominator. I'll just abbreviate to LCD for least common denominator. Then subtract. And why do we have to do that? Well, the limit is, once again, going to an inconvenient spot. If it's going towards 0, that would become a 1 divided by 0, and this too would become a 1 divided by 0. So this one is undefined minus undefined. You can't do any arithmetic with undefined. So we need to do some work on this just to start it out. And it's even a little bit rougher than it seems, because in finding the least common denominator, the next thing I would want to do to get this is first factor all denominators. That gives us the cleanest approach into producing the least common denominator without getting too bogged down, getting a common denominator that's of degree way too high, which makes us simplify a lot more in the problem. So let's scroll down to this point. To start this problem, it's not as bad as it seems. We just have to review how it's all going to go. There'll be the limit as a variable t goes to 0, often representing time if we see t. I'll put a big parenthesis like this. The denominator here is in its factored form, it's just t, but make this a bigger fraction because we're going to be adding stuff above and below. So 1 over t minus, it probably didn't have to be that big, but let's go with that. Here, this is where we're going to factor. Just pull out the greatest common factor, which is t, and that leaves behind a t plus 1. And these problems are kind of weird in the sense that we don't always directly say what the least common denominator is when we solve this. We just produce it and move on to the next steps. Notice that there's two kinds of denominators. There's one that involves t, and there's another that involves t plus 1. Think first in terms of we want common denominator. Least just means the degree should be at its minimum so we don't work too hard on this. Factoring is going to give us the least common denominator with what we're about to do. And now we just have to make the denominators exactly the same. Something's got to go in that spot. Anyone see what it has to be? Absolutely. We can put a t plus 1 right there. We just have to be mindful that I just broke equality right now, unless you put it in the numerator as well. So there it is, above and below. The moment we did that, we have the least common denominator. It's been produced. We don't have to say we found it, but just for the sake of reference on the notes, we now know the least common denominator is t times t plus 1. So with that, we can just subtract cleanly across the numerator. We're multiplying by 1, so we can drop the parenthesis there. Sorry, I said that wrong. Not multiply. We can subtract across the numerators and maintain the least common denominator. So this is going to now be the limit as t goes to 0 of t times t plus 1. Let me color code them again just to show where they came from. There's the common denominator duplicated. And across the numerator, this is t plus 1 minus 1. And that means we're on our way with this one. We have like terms, we can cancel plus 1 and minus 1. Just annihilate each other. They undo one another. Now it's a limit as t goes to 0 of t times, or excuse me, t divided by t times t plus 1. Same kind of stuff as we've seen before. Some people might have already spotted the limit, but to get there in stages, here's at the stage where I would start to cancel. This t and this t cancels, leaving a 1 in the numerator. And I always put this 1 here because even though it kind of sounds silly, sometimes when I cancel a t like that, I forget there's a numerator at all, and I accidentally bring this t plus 1 in without the fraction, making it not be a denominator. So this is just a reminder for me that there's still a numerator even after canceling. Now its limit, t goes to 0 of 1 over t plus 1. We could do direct substitution here until that t was gone, but now we can. There's no harm in directly substituting in a 0 value right there. Well, we've got it, folks. Looks like the limit is 1 on this one. We go to the next step. It's 1 over 0 plus 1. And so the entire limiting value just turns into a 1 directly on this one. Algebra probably feels the most intense on this one, depending on the student. Some people probably were possibly less a fan of the conjugates versus this one. I think most people feel like this is the nastier version. I think there's one just like this one on WebAssign. So you can always go back here on the notes to see what some strategies might look like. But also, if you're getting bogged down on algebra, if you're not sure how to proceed, don't ever hesitate to hit the Ask My Instructor button. I'll be happy to help out. Marie says, there is alternatively, couldn't you solve these problems by substituting 0 with a number close to 0, such as 0.0001, and rounding the answer? Yeah, occasionally that can work out for a lot of these different kind of problems. There's one small danger with that approach, though. It's entirely plausible that, say, in a different kind of question, the limit comes out as 7 divided by 10 power 6. Just depends on the context. So then it becomes a bit of a guessing game. Did we make our substituting value close enough to 0 to see exactly what the true limit really is without having to do any kind of rounding? Or if the value was even worse, maybe the value to the problem was, say, pi divided by 10 power 6. Really inconvenient number, say it's, let's put it in the calculator just to see how inconvenient it really is. It's entirely plausible that in a problem, a limiting value is this one. And we would have to decide, how do we know when to stop? How do we know that we really produce pi over 10 power 6? Usually for these kind of problems, the easier approach is maneuver it through in this kind of way, use the limit laws, direct substitution, and we pick up the problem direct exact answer in a more faster approach. So yeah, it's true. Some of these problems weren't too bad, like coming up with a direct 1, a -10. First problem of the day might have been trickier. You would have had to produce 3/7. So using that approach, taking values closer and closer to -3, you're getting values like this, for example. But the answer that we're going for is the dead on exact 3/7 is the number that solves this one exactly. Since we're going for exact values, this problem would have been really tough with that approach. But you're right, we could get pretty dang good approximate values, but I would not know when to stop getting closer and closer to a -3. So I have enough values on this decimal expansion and then do the additional algebraic work to convert it back into the actual exact fraction 3/7. So sometimes it's a quick technique, but in general, usually algebraically, quick factorization cancellation is the better way to go. Does that make sense with that question there? Awesome. Other questions at the moment? Okay, well, this is pretty much the guided tour of the kind of problems you're going to see in the WebAssign homework. And also, it's pretty similar to the problems you're going to see on quiz number 1. So give these a try. If you find something that's coming out wrong, don't hesitate to double check it in a graph as well. See what it looks like visually, because again, connecting the dots, seeing what these look like from two different sides is a great way. And if you have questions, don't hesitate to ask. I'll be happy to help out. Ask a classmate if you're working in groups. I'm available in office hours. Questions by email are always great as well. In fact, one thing that everyone is welcome to do is, if you're working digitally or on paper, and you wrote out the problem, you can just send me a screenshot or send me a picture of that work directly to my email and ask me about it. I'll be happy to engage with you. Maybe you got stuck at a certain step, show me those steps, and I can work with you on them. Pretty much just annotating it just like we're doing here on the lecture notes in your email. Well, we have one last problem since there was a promise at the start of the course. My goal with the lecture notes is try to put in an application problem on every single one of the lecture notes. There might be a set of notes here and there where I just can't quite seem to find one that fits in really well, but I should be able to do for the vast majority, overwhelming majority, an application per section notes, which seems fair. We shouldn't be learning a whole bunch of pretty abstract calculus techniques if we can't see how it connects with ordinary reality. So here's a pretty reasonable scenario. We have a biologist studying a specific strain of bacteria in a petri dish. Maybe it's E. coli, something like this. Maybe it's a food safety kind of research problem that they're interested in. We're told the growth rate of the population is stable. Oh, by the way, a petri dish is just a little dish of gelatin type growth material where the bacteria is going to grow in, if you're curious. Now, just to make the problem feel a little bit more real, let's take a look at that. It's kind of a weird word when you think about it and you say it in your head 10 times. Petri dish. Something like this, these little plates where you have a growth material, you dab your bacteria inside of there, and you watch how it grows. And people can count the exact number of cells in a dish like this. What they do is they put it under a light. There's a sensor above where the light is coming in, hitting that dish. And for every photon that's blocked, the assumption is a bacteria blocked it. So that's a count on the bacteria growing in the petri dish. Pretty crazy laboratory experiment when you think about it. So we're growing some strain of bacteria in a petri dish just like that one. We have a stable growth rate, but they introduce a limited time enzyme that temporarily disrupts the reproduction cycle. So reproduction is disrupted, That means probably the population is going down. Now they say using experimental data. What do they mean by that? Maybe they opened Excel and at time 0 seconds, they did a count on the bacteria. Then maybe every 30 seconds, they did another count, found out the bacteria. And now they have all these dots and they fit a function to it after they looked into the scatter plot. Here's the function. It's just a model of what they saw. This is a model of the population size. At time t. So P is going to be the amount, the population size of the bacteria in thousands. T is going to be a measurement in hours after the introduction of the enzyme. So when time is 0, that's the initial size of the population. And the biologist wants to know what will happen to the population as time gets closer and closer to the 4-hour mark. Well, probably what the biologist would do if they came up with this mathematical model is just plug it into a calculator. So they would have written out P of t equals t squared minus 16 divided by t squared minus 3t minus 4. Here's the whole graph, but this has a context of time 0 is when the actual population modeling takes into effect. So they introduced the growth rate limiter, and now the population is falling. We are curious of what happens at the 4-hour mark, so we can calculate P at 4. But that's a problem, it's undefined. And so now we have a weird problem. We expect a number, it's about right here, whatever the height is. We need to calculate it, but we can't plug it in to get the value. So what we'll do instead is find the limiting value. We want to know what will happen to the population as time gets closer and closer. That's kind of a buzzword. We need a limit to find this to the 4-hour mark. So let's highlight that and mention from this part right here, we need a limit. The context didn't imply a direction, so we're going to take a double side limit and compute the limit as time gets closer and closer to 4 hours of the population function P at t. So this is what it will look like. This is just a statement of the problem, but now we're going to substitute inside the function. Limit as time gets closer and closer to 4 of t squared minus 16, t squared minus 3t minus 4. So we want the value of this limit now. Well, this is really just kind of a rehash of the problems we've done so far on example 4. If you see a polynomial divided by a polynomial, and we know we can't plug in 4, we got undefined in the calculator, probably our best next technique is just to factor this one. Numerator will factor as a difference of squares, so let's get started with that top value. We have the limit as time gets closer and closer to 4 hours. These are always kind of nice. If you see a negative sign with 2 different terms, t squared minus 16 means you can go t plus, t minus. 16 is a perfect square, so try with a 4 and a negative 4, and actually that's guaranteed to work every single time. You could verify this by foiling it out. Middle term cancels, just like with working with the conjugate. Down below, this one's a little bit more challenging to factor, but it's not too terrible of a factorization problem. We can go t and t. Negative there says go with a positive and a minus. And to get to negative 3, we should make our 4 go here, be a negative 4, and throw in a plus 1. So now those values multiply to the negative 4, they add up to the negative 3, and so that's our complete factorization. And again, it probably feels like deja vu. After we factored, we can now immediately see what cancels. It's the t minus 4 above and below. And with those gone, you are ready to make a direct substitution. We can do it right in this step if we like and get a value out. Any questions to this stage of the process? Okay, Well, let's plug it in right at this step. We plug in 4 in the numerator. For the denominator, here's what it will look like, highlighting just to show where that direct substitution happened. And so this comes out as 8/5 altogether. You know, this is an applied problem where maybe a fraction doesn't make the most sense, so it wouldn't be any harm in this context to just put in 8/5 and get a 1.6. I'll leave it up to your call. I'm not going to be too picky. But I think this might look a little bit more cleaner to call it a 1.6. Go back to the unit. This is in thousands, so we can say 1.6 thousand bacteria are the amount that would be present as we get closer and closer to the 4-hour mark in this function. So it's kind of a weird model. It had an undefined value right at the time of interest. Maybe that's why we're investigating that particular time, because the model had a problem there. But this would be our expectation. And they could check it by rerunning the experiment, see how close they get to 1.6 thousand bacteria. Well, it's just a model. They might not get exactly 1.6 thousand each and every time. But I bet you if they ran the experiment 10 times, and this is a really good mathematical model, the average outcome is probably going to be pretty close to that value that we just found. There's always a little difference between what we see in reality versus what happens with the pure mathematical function. So that mismatch is just the accuracy of the model that we produce in the first place. Well, we did it, folks. That's the rundown of doing limits so far. Any questions or comments at the moment? Yeah.
For a question like this to be in the fraction, it does.
I think WebAssign is actually pretty forgiving with the number type. It usually accepts both for these kinds of problems. And they even print the units for us, so there's less worry about the unit as well. So yeah, WebAssign would be accepting both. If it's a number that maybe came out, say like forgot what the value was, but 3/7, for example, oftentimes it would indicate a place to round to, or if you just gave it the direct fraction, it would take that result as well even.
You know, round like how number units it looks like.
It would always ask in the WebAssign for the rounding on these things.
Okay.
This one, I didn't actually say what to round to because it came on as a dead on exact 1.6. But yeah, WebAssign is pretty specific on the rounding as well, which is another one of the reasons actually, now that you mentioned that I accept a limited tries on the WebAssign homework, because sometimes when they say round to 2 decimal places and the answer is 1.57, but you said 1.58 just on mistake, they sometimes mark that as incorrect, and it's extremely frustrating. So if that ever happens to you and it's just a rounding error, I go back and I just respond, oh, that was just rounding. You did the right problem. They're expecting this number. So it's not going to be as much of a headache. Other questions so far? Okay, well, we finished section 2.2, limits. There's lots to talk about on this one. And the very next section already, sorry, let me go back to Canvas, is continuity. I felt like with the amount of time we had, it might be a good idea to go back to section 2.1 to end the day and explore the topic that we started out class with just a little bit in our current problem. The question people might still have at this moment is, how in the world does taking limits like the ones we've been doing so far get us the slope of the tangent line? So let's investigate that a little bit further with the limiting knowledge that we have so far. Let's put this back on our notes. Let's say that this is additional comments. For any calculus course, it's really important to say why we're working so hard on limits. It's a weird mathematical topic, but it's all about that slope right there. So let's show how the limit process actually comes into play. Then when we come back next week, we're going to delve into section 2.3, and that's going to move us into chapter 3 right after, finding these values for the slope. So here's the next thought. If you want to get the slope of this line that you see right here, you need 2 points in a certain sense, right? Because that's what our slope formula looks like, rise over run. is going to be change in the distance, y coordinates, divided by change in time, horizontal coordinates, the t coordinates. So we'll place in another point. Let's put it right here. I want it to be close to A, so what we'll call this is A plus H, where H is a small value. So add just a little bit more to your original value A to get A plus H, and you get a new point right up here. That means you have a different kind of line. It goes like this. So imagine that's a perfectly straight line going that way. It's not the tangent line. It actually has a new name called a secant line, not as secant as in trigonometry, for example. But with that secant line, we can approximate the slope. We can now say m is approximately equal, not directly equal to the change in the function values. So let's write this on the y-axis just to really explain. The y-coordinate right here, go horizontally to the left, will be f at a plus h. So that's one y-coordinate. Divide by this y-coordinate. This one will be f at a. They're pretty close to each other, and these are our two, I don't want to say x-coordinates, this is in time. These are our two horizontal coordinates. So let's write it out this way. We're going to say y2 minus y1 divide by, instead of x, I'll call this t2 minus t1. This is just the typical way we write down the slope. But we're going to get our values from right up here. This one, f at a, is going to be y1. F at a plus h is going to be y2. Likewise, this is going to be time 1, the a value. This will be time 2, the entire a plus h value. So this will turn into, in place of y2, this is the f at a plus h. That's an h there. Minus, in place of the y1 value, it's just a f at a. Now for t2, that's going to be a plus h. Minus the t1 value is just an a. And so this is just ordinary compute the slope. It's got function values inside because we have a function we're working with. And notice what happens in the denominator. A cancellation out of nowhere. It's just h in the denominator, which we think of as a small value. And this is going to be f at a plus h minus f of a divided by h. So that's our slope formula all the way over here, connecting the dots, making the substitutions with those four values off of the graph. Only problem is it's approximate. But you know what? We can improve that approximation. Any volunteers to say a way to make that approximation better? Sorry, say again? Yeah, absolutely. If we take a limit by making h smaller and smaller and smaller, what would happen is the a plus h gets closer and closer to a. You can't let it be a because you've divided by 0. But remember, in the limiting process, we don't care what happens directly at the point a itself or when h is 0 directly. When a plus h gets closer to a, the secant line, I drew it in two parts, but imagine this dot is getting closer and closer to the black dot. It becomes closer and closer to the real tangent line. So what we'll do to calculate the slope is the following. M, the slope we really want, and we want to compute this exactly, will be the limit as h itself goes to 0 of f at a plus h minus f at a divided by h. So this is where all of our work so far in these notes connects back to the original problem we wanted to solve, computing the slope of the tangent line. Well, any questions about that so far?
That's still what we're just working through, right?
Exactly. We have one more section to get through, 2.3 on continuity. Just a little bit more topics on taking limits. Usually, a good way to think about that is more topics on direct substitution. That's what continuity really is all about directly. Then, with all the material we have about limits under our belt, we'll be able to attack this problem right here. So this will be the chapter 3 problem. We will solve. Well, any last questions or comments at the moment? Okay, when we come back next week, we'll take a look into what's going on with the continuity section. Really, it's going to be more material about like this. And so for where we've ended out so far, probably what I'll say exam 1 is, and I'll finalize this before we come back to class next week. I'm thinking for exam 1, it's just going to be sections 2.1, 2.2, and 2.3. Same kind of problems we've been doing in notes that you've been doing in WebAssign as well. But have a great night, folks. We'll be back to this next week. Thanks. Have a good one.